Now we're going to look at how software instructions inserted in the application can help optimizing with respect to caches in a system. If we look at just a simple loop here, nested loop, we access all the elements of an array. And if we know that these accesses to the array would miss because this array is larger than the cache, we could opt to insert certain software prefetch instructions. These are not typically supported in high-level languages, so we would have to insert some kind of assembler intrinsic or some other assembler code. Here it's simply just represented by a macro that would expand to such an insertion of assembler instructions. So what we do in this example here is that we bring in the elements of this array that we are about to access in the next row, j plus 1, when we are accessing the element j. And hopefully what that software prefetch instruction will do is to instruct the memory hierarchy to bring the data into the first level cache. And hopefully once we get to that next time we get to the j plus 1 iteration of the outer loop, that piece of data will still reside in the first level cache and will turn that compulsory miss to that piece of data into a cache hit. So for this simple example here, what I'm showing is a strided access, or actually a very sequential access to memory. So we already know that the hardware prefetcher will be very successful at accessing, or rather prefetching, the data that we would like to request soon again. Question remains, are there examples where software prefetching can do better than hardware prefetching? So we're going to look at a couple of such examples, and we're going to look at some of the research that goes on in the architecture group in Uppsala. The first work we're going to look at is how to reduce cache waste. So first we're going to look at the general example, and then we're going to go in and look at the research result itself. So if we look at this kind of two inner loops sitting in a outer loop that goes on for many iterations, and the first of those loops accesses a huge data structure, much larger than the cache. That means that we will actually flush all the data that might have been in the cache when we go in that loop. And then we have another loop, which is a smaller, fewer iterations, goes in a smaller data structure y. So after we are done accessing the red accesses to y, we will have the data structure y residing in a second level cache. Then we go out again and start to access the blue data structure, which is larger than the cache, which means now we will flush the entire cache, just put blue stuff in there. We come back and we access the red data structure again, which once more will cause lots of cache misses. This does not look like a very optimal way of using our resources. So it would have been much better if we access these two data structures in two different ways. And what we're going to choose to do is to access the red data structure in just a normal way. We're going to use normal load instructions. So once more, what do load instructions do? And this example is an exclusive inclusion property of a cache hierarchy. In such a exclusive cache inclusion hierarchy, you perform the load. That means the data will be installed in the first level cache. Upon eviction, it will be replaced to the second level cache until it may be evicted from that cache. In that case, it is put back in memory. In case it's dirty, otherwise we'll just toss it over our shoulder. So that's the strategy. We will keep using the normal strategy we'll use for the red data structures. But we will look into an alternative access strategy for the blue data structure that we know will not fit in the cache at all. We will use a strategy called prefetch NT. So this is a specific prefetch instruction that has been extended with non-temporal marking. That means that we are prefetching data that we think would not be beneficial to put in the cache at all. So here, the prefetch NT will bring the data into the L1 cache, but upon eviction, it will not install it in the L2 cache, but it will rather write it back to memory in case it's dirty, or just toss over its shoulder if it's not dirty. So this is how we would use that optimization in the previous example. We will simply insert prefetch NT instructions to our accesses. And as you see here, we don't leverage the fact that we actually may choose to prefetch data before it's been used. In this example, we just prefetching data in the prefetch NT in the same iteration that it's being used. So the fact that we do bring the data into the cache using prefetch NT means that that data will be tagged as non-temporal data, and the replacement strategy when it's evicted from the L1 cache will be to simply bypass the L2 cache and instead put the data straight back into memory. So if we have this strategy, that means that the blue data, the red data will be able to reside in the cache, and since the blue data will always bypass the second level cache. So here's a question that you may all have been expected at this point. What kind of misses are removed with this strategy? Do we remove capacity misses, conflict misses, or compulsory misses? Well, it's actually capacity misses, since the cache is not large enough to hold both blue and red data in the cache. But with this strategy of choosing not to put the blue data into the cache means that we can still find the red data in the cache even though the cache was small enough. This kind of strategy can also be beneficial not just when you run a single application like this fairly constructed example here, but more so if you run many applications together and those applications are scheduled to run in the same multi-core, which means that they would most likely fight for some cache resources at some level in that multi-core. We're going to see now how you can apply a automatic strategy for inserting these kind of prefetch NT instructions into the code. So this is work done at the UART group, and it's done by Andreas Sandberg. He published this some 2-3 years ago at Supercomputing. And what he said here is that if you have many different CPUs running, you can leverage the fact that you have different kind of prefetch strategies and well as access strategies. So for example, you can have normal loads, as we saw in the previous examples, that upon eviction will put the data in L2 and then back to memory, or you can choose to use prefetch NT. In that case, the data is installed in L1, but upon eviction, it bypasses the L2 cache. If we have the same kind of miss ratio curves as we have looked at several times now in this software optimization part of this course, if we had that kind of information about each application, and we know how large the L2 cache was, that's the size of the L2 cache, as well as the size of the L1 cache, we could look at those curves and we can ask ourselves questions: which instruction make accesses to data that has a too bad locality property for being accessed again while it resides in the L2 cache? So if we can find instructions that bring in the data, the hopeless data that would require a larger cache than L2, then we can automatically change those instructions to become prefetch NT instructions. And that is such a scheme that Andreas has used to automate this process. So there are two components to this. One is the fact that we can actually very inexpensively find the shape of this curve. And here we will rely on exactly the same technology that went into the thread spotter tool that we discussed before. And the second part of this is Andreas' heuristics that finds data, or rather finds instructions that access data here, and also make sure that the data that's being accessed have exactly the right properties that would make prefetch NT a good fit for them. So automatically makes changes to applications using this. And here we can see the results. So we see how the results from applications running on a 4-way multi-core system. So we're running on 4 CPUs at the same time, where the CPUs share cache at some level. The blue bars is just the reference bar that shows how fast each of these 4 applications run when they run in isolation. So they run one at a time, and they can actually harvest and benefit from the entire L2 cache because the other cores are completely unused. The blue bars shows how much each application slows down when they are run together. So on average, they slow down 25% when they run together. And the green bar, actually more, 30, slow down more like 30% when they run together. And the green bar shows how fast they run when Andreas has applied his automatic modification to them. So that's the patched version of those applications. You can see they run about 25% faster in his automatic modification to the code. So once more, this is an example where Andreas has managed to avoid capacity misses in the caches by finding the instructions that waste space in the L2 cache and making sure that those instructions will bypass their data, so they will not have the data installed in the L2 cache. Here's another example of how you can use some of the modeling technology we developed at UART to do an even more general insertion of software prefetches into code. So this is a work that Muneeb has done. So once more, we use the UART modeling technology that was used for thread spotter. It's called StatStack, and we'll discuss that later in this course. And we use this technology once more to understand the application, understand which instructions access data with good locality and which access data with bad locality. This tool runs at the overhead of only 20% over native execution when we collect that kind of information. Then we identify the instruction that miss in the cache. Okay, that seems like a good idea if we're going to insert software prefetches. We capture the stride that these instructions have between their accesses to data, A plus 7, A plus 14, A plus 21, and so on. That could be an example of those strides we find. We also figure out the necessary prefetch distance. So we figure out if we need to prefetch the data one iteration ahead of time, two iterations ahead of time, and so on. So when we insert the prefetch instructions, we need to know how many prefetch distances ahead of the current access we need to prefetch the data. And we also try to figure out the best non-temporal strategy. So he leverages the work that Andreas Sandberg did to automatically say whether or not we should do a normal prefetch or a non-temporal prefetch. And then at the end of the day, he performs a cost-benefit analysis to figure out if it makes sense to insert a software prefetch instruction into the code. If so, he will do it automatically. He will insert the right prefetch instruction with the right stride and the right prefetch distance. And ideally, you would do this, insert this directly into the binary. But in this example, he's actually inserting, he's rewriting the assembler code automatically. So we don't even need to have the source code to make this change. Here's an example of how well that works. So we're looking at AMD Phenom 2 processors, and we compare the existing hardware prefetching, aggressive hardware prefetching that's implemented by the AMD engineer in the chip, and we see what speed up we have if we use that prefetching for some number of common benchmarks. These are the benchmarks that put a lot of pressure on the cache system, so they really do benefit quite a lot from this speed up. So you can see hardware prefetching can get you as much as 50% speed up. On average, we will get something like 18% speed up. And then Muneeb turns off hardware prefetching and completely replaces it by inserting software prefetch instructions automatically into the code. And you can see on the average number here, he gets a better speed up than you get with hardware prefetching. So that's good news. Doing the same experiment on Intel Sandy Bridge, doing the same experiment on the Intel Sandy Bridge, we get a similar number, but here the hardware prefetcher outperforms us by a little bit. So these experiments are run in such a way that you run a single application on a multi-core at a time. So that application can use all the second level cache. It can also use all the bandwidth to DRAM by itself. And that is why sometimes the hardware prefetching can actually do a pretty good job. But you can also see on this chart here, which looks at how much the data volume increases when you turn on hardware prefetching compared with when you have no prefetching at all. You can see that, for example, for GCC, hardware prefetching moves 50% more data across the DRAM interface than if you have no prefetching at all. Ideally, an efficient prefetching algorithm should not increase the data volume at all, because the DRAM bandwidth is a very scarce resource, and also moving data across the DRAM interface burns a lot of energy. Muneeb, on the other hand, manages with his prefetch scheme, he's much more resource aware, so he makes sure that, and he can use the modeling technology here to really make sure that if he inserts a prefetch, that he's almost guaranteed that that piece of data is indeed needed. So the bandwidth increases just a little bit. The worst application in his example, A star, increases the bandwidth of 21%. The worst example for hardware prefetching is 251% data volume increase across the DRAM interface. For Cigar, there should be a good old friend of yours by now. So clearly, we don't have an average to compare, but you can clearly see that Muneeb's numbers, so that's the gray bar, compares very well with the black bar. In parentheses, this bar over here is another kind of software prefetching algorithm that somebody else designed, and Muneeb is comparing with just to show that he's more resource lean than they are. It's also interesting to see that in some situations he actually can transfer less data volume. And here's a good old friend of yours again, LBM, Lattice-Boltzmann method. And here he can actually rely on successfully inserting non-temporal prefetches that allows him to actually reduce the amount of data he moves from the DRAM. Looking at Sandy Bridge, well, the result looks slightly different. Sandy Bridge is a more aggressive hardware prefetcher, which means that there are more situations where it consumes more bandwidth, and we consume about the same amount of bandwidth in our case as we did in Sandy Bridge, as you should expect. Now, if we start to run several applications at the same time on a multi-core, you get a comparison that looks like this. So and this is comparing numbers for Sandy Bridge. So what you see, the blue line here is how much Speedup Muneeb gets for a large number of different application mixes that we have tried out. And he sorts his results from worst to better. And then he puts the corresponding number Speedup you will get using hardware prefetching and compares that. And you can see that on average we do much better. There are situations where we do worse, few of these mixes, but on average we do substantially better than if you only use hardware prefetching. And once more, in Muneeb's case, we turn off hardware prefetching and just uses his inserted prefetches. On the right hand, you see the data volume in these situations where we have application mixes, and here you can see that consistently Sandy Bridge uses much higher volume. This volume is lower than in the previous examples. We don't see any 600% or 200% increase here for any applications, and that is because hardware prefetching is sort of smart. So when hardware prefetches senses that we are running out of bandwidth, then it will throttle itself down, or maybe sometimes completely turn itself off as well. That means it will not use so much bandwidth, but it also means it's going to be less successful in providing speed up. So that's why we actually managed to beat it in this example. So average number for Sandy Bridge is an increase of 20% of the data volume moved, while in our case we actually on average move less data than if we don't have any prefetching turned on at all. Same comparison for AMD. Here the difference in speedup is larger. is about a 10% improvement for us over the hardware, just using the hardware prefetcher. And data volume wise, in this example, we actually do increase the data volume quite substantially. I don't fully understand why, but it was still below what they use with their hardware prefetcher itself. Finally, the work that Muneeb has been doing has also been extended to do non-strided prefetching. So if you have pointer chasing, or if you have objects or nested objects or indirect accesses, as you would often have these days from high-performance computing, he has a way of automatically handling that as well. Once more, he is applying his changes at the assembler level. Eventually, it will be binary modifications, and he will not need access to the source code to apply any of those changes.